Okay, so today we're going to talk about binary trees. Up to now we've talked about essentially two data structures, an array and a linked list. And hopefully you've noticed that there's a couple of shortcomings to both of these structures. Namely, with an array, if you need to insert in any given order, you usually have to shift. In a certain position, you got to shift everything down. Linked list doesn't have that problem where you have to shift everything down, but you still have to find the location, which means you have to traverse through the linked list, which also makes an O of N operation. Binary tree is going to at least alleviate this problem by making insert, at least in an ordered fashion, a lot faster. And it actually has a couple other nice properties as well that we will get to. All right, so binary trees. Right, we're going to learn about binary trees, the different traversal algorithms, organize data, insert and delete, and then talk about different traversal algorithms. We're going to spend 2 days on binary trees. So today we're going to pretty much talk about traversal, what a binary search tree is, which we're going to talk about first before we do traversal. And then we're going to talk about insert. And then afterwards we'll talk about delete, because deleting is a little more complicated. Additionally, your project 3, which I will assign on Wednesday, will be to basically do a comparison of different binary search tree implementations. So pay attention to this. One thing to keep in mind is on that project, I am going to allow you to really go out and copy and paste code from the internet, so at least have that going for you. But make sure you understand binary search trees, because they're going to be vitally important, especially for project 3. Okay. So I've talked about why they're somewhat important. So a binary tree is either empty, okay, great. Like a vector could be empty, or an array could be empty, just like a linked list. Or it has these properties. It has a root node. So we're going to have a starting node. And then it has two sets of nodes, the left subtree and the right subtree. And left and right are binary trees. What type of definition is this? It's a definition. I'm trying to get y'all used to thinking in a certain word. You haven't thought of it this much because you haven't probably done discrete math yet, but what type of definition is this? Defines a binary tree, and then inside it says we have other binary trees.
Like recursive?
Yeah, recursive. So anytime a definition contains the definition within itself. Good morning, Jonah.
Good morning.
It is recursive. I think a picture is really going to deliver this. First off, keep an note that these pictures down here with the arrow and the lot of lines, that is null, aka nothing, pointing to nothing. And each of these values or circles contains some value. So the root node has the value A in it, and it's a parent of B and C. Binary tree likes to use this terminology, parent and children. So the root node is a parent of B and C. Why is that? Well, it points directly to B and C. Can anyone guess why it's called binary by looking at this picture? Split 2. Namely, it has how many children? 2 children, hence binary. Ah, got it? All right. We're just going to stick with 2 for now, because going beyond 2 actually gets pretty complicated.
So if you call it a trinary?
Could be a trinary tree. A quad tree is actually very popular in 2D graphics, and an oct tree is very popular in 3D graphics. But we're going to stick with 2D binary trees, because otherwise it gets very complicated very fast. All right, notice that so you have 2 children, and that's a directed edge. So once you're at a parent, you can only go to your children. You cannot go back up to your parents. There's no two-direction branch or edges here. So notice that C, while it can have 2 children, only has 1 because the other one is pointing to null. By the way, I'm saying, what does that mean that these 2 arrows really are? Pointers, right? So these arrows, if you want to think of it practically, they're actually a pointer. So each node has 2 pointers, and they either point to an actual node or they point to nothing. All right. Let's see what else we got. So how many nodes are in this binary tree? 8. Can anyone tell me what the height of this tree is?
4.
4. Why Why does it have a height of 4?
Because there's only like 4.
4 levels, that's correct. Another way to think of it, it's really, they'll say a height of 3, because that's, if you find the longest path going down, it has 3 edges. Or you could say it has 4, because the last edge points to null, depending on how you want to define it. All right. So here's some other binary trees, just to get started. A, which is one node, has 2 children. Both point to nothing. The second one, A, still has 2 children, technically, but the one points to nothing, so it really only has 1 real child. But B also has no nodes, so it's the termination of it. And then the second one, you have C, and then you can combine the 2. One last definition I wanted to talk about. If a node, both of its child pointers are to null, we call it a leaf. Do y'all see it? What is that? You get it? Right.
Ends.
It's at the end, right? Because you don't put leaves on top of leaves. A distinct branch. Yeah, you got it. All right.
Not a leaf, just a power of leaf.
It's got leaves. All right. We can continue on with different binary trees with 3 nodes. These are all legal binary trees. What's the height of each of these? 2. Or no?
Well,
Or 2 or 3, yeah, 2 or 3. And how about the last one here? Height of 1 or 2, yeah, depending on how you wish to look at it. So hopefully you can see. Morning.
what you got, Mac? It's empty.
All right. So every node has at most 2 children. So a node has to store its own information, it needs to keep track of its left subtree and its right subtree using pointers. All right. What else had 2 pointers per node?
Doubly linked list.
Doubly linked list, but what did those point to?
Back.
Backwards and forwards. Now, we're not pointing backwards and forwards, we're really only pointing forwards. We just have 2 forward pointers now, if that helps you any. It probably would confuse you, but just trying to show you how some things connect here. So here's a little better picture. Root. Notice that you have a variable root that points to the first node. That's in case your binary tree is empty. You can have point to null, and therefore you're done. But then the first root node A, 2 pointers to B and C. Maybe B points to D and E, and D points to empty or G, and then G points to nothing else. All right. Any questions on this picture so far? Nothing yet? All right. So the leaf, we said, it has no children, like the leaf of a tree. A parent of V is if there's a branch from U to V, aka a parent of a node is directly above it. All right, point 3. There is a unique path from the root to every node. Does that seem obvious? Can anyone explain to me why that, at least intuitively? This is not a math class, so we're not going to prove it formally. But why is there always a unique path from the root to some node?
Because there's only one way to get to it.
It's only one way to get to it, right? But that's actually what I'm asking.
Oh!
No, that was good. That was good. That was
That's
good.
what I thought you were like, why? Okay.
Yeah. So why is there only one path? Is it possible for there to be a cycle? No. Do you know what I mean by a cycle? Maybe A goes to B, B goes to E, and then E loops back up to A. That'd be a cycle, and then you'd have multiple paths. Or maybe you'd have E loop over to C, and then to F, and you'd have 2 ways to get to F. Both.
There's only one way.
But there's only one way from this picture, right? I'm saying if this A pointer looped up to C, then to get to F, you could go A, C, F, and then you go A, B, E, C, F as well. If this pointer pointed to C. But we're not allowing that in our binary trees. So whatever I just told you, if that was confusing, ignore it. But I just wanted to make sure you understood that it was unique. Good morning. All right, so the length is the number of branches, and then the level is the number of branches on the path from the root to a node. So we're going to say a root node has level 0. And then height, we explain that number of nodes on the longest path from the root to leaf. So the book is going to go with height being the number of nodes. So what's the height of this one? 4. Right, so we're going with number of nodes. Right, not number of branches, number of nodes. Okay. Before we go into the copy tree and whatnot, I think it's very important to get to the whole point of binary search trees, so I'm going to skip ahead with a lot of these notes. So first off, let's say we have a tree with a bunch of numbers in it. If we want to determine if 53 is in here, what do we need to do? Search. How would we search? What do we do?
You have to like choose a way each direction.
Right, so we have to go every direction, which means we have to visit every node. How does that compare to our previous data structures, linked list and arrays? Does it improve upon it, or does it?
Seems like it'd be slow.
It'd just be as slow, right? So binary trees are not done this way. They usually have an ordering to them. Can anyone guess what the ordering is going to be?
Log of n.
Log of. You've taken this course before. No, that's the algorithmic complexity of it. But how are we going to order the binary tree to get a log of n?
Just like make the smaller children on the left, bigger children on the right.
Right. So whenever you add a node, everything less than to it will be on the left if we choose that ordering, and everything else that's greater will be to the right.
So if you had, it was pointing at two numbers, you would put it in the middle, higher.
Right. So the idea is that when we start adding them, if the tree is empty, we'll get to inserting in a moment, but if it's empty, you just add it, and then afterwards, if you want to add another number, like up here you had just 60, you want to add 50, you visit the first one, am I less than or bigger or greater than? I'm less than, so let's go left. Oh, that one's empty, we'll just add that node there. So anything larger than data is its low. Everything less than the number is to the left, and everything greater than is to the right. Why is this more efficient?
So now you could just search one side as opposed to every node.
So what type of searching have we basically enforced by keeping our data structure this way? Which two searching algorithms did we have? We had linear and
Binary.
binary. So yeah, binary. So which one is this following?
Binary.
It's similar to binary, right?
Sort of.
Right, because we have a sorting to it, and so we can divide it in half like binary search. And what was the algorithmic complexity of binary search?
Log of n.
All right, so hopefully we can get a log of n out of this. And that's really the main point of using a binary search tree especially for this class, is to try and divide it out so that we can maintain a log of n searching algorithm. All right. All right, formal definition. This is similar to the last one. It was recursive. The only thing they added is that step 3, where every root node is larger than every key in the left subtree. AKA, you have this ordering where everything left is less than and everything to the right is greater than. Okay. Now, I think we're at least to the point where we can code this up. But before we do that, I want to, we'll code it up first. A lot more fun. Good morning.